Well, on this channel, I talk about science and its human dimension, about how hard it is for new ideas to break through in science sometimes. Because colleagues surrounding innovators, as a rule, do not accept this new thing, because a revolutionary scientific idea always seems too wild. And often, a new scientific paradigm only takes hold in science when the old generation, set in its ways and errors, dies out. The generation that defended its theses under the old paradigm and spent their whole lives getting paid to teach it. That is how our biology is wired. We are animals, ladies and gentlemen. And in this sense, mortality, by the way, is the engine of progress. When humanity achieves immortality, it will stifle progress, plugging it with a cork of immortals who are accustomed to old paradigms. If we were immortal, we would still be jumping through the trees. And what is most surprising is that new ideas in science often struggle to break through the psychological habits, even in the minds of those who discovered them. And this concerns that tragic story from the beginning of the last century, when physics lost everything it believed in, objective reality itself. Let us examine this through the example of two titans, with whom this entire collapse of reality and the transformation of physics into Zen Buddhism began. With Max Planck and Albert Einstein. Which of them is more valuable to the mother of history? They overturned the edifice of physics by undermining it, right? They broke everything they themselves believed in, and that tormented them for a long time afterward. But they were the ones who planted a bomb under the real world, or rather, under the world of physical realism. We could use a different metaphor and say they laid the cornerstones for the foundation of quantum mechanics. Bombs and cornerstones are different things, but they laid both. And yet, for the rest of their lives, they never truly believed in what they had done, nor in the conclusions that stemmed from their own work. And both of our heroes today, by the way, were similar in more than just that. They were both also musicians, which for some reason few people know. Max Planck, at one time, was choosing his life path and wavered between music and physics. He wrote good operettas and played music excellently. Einstein, by the way, just like Sherlock Holmes, played the violin in his spare time. Well, a Jewish boy. By the way, they sometimes got together in their Germany and performed duet-home concerts for guests. Max Planck would jam on the keys, his pince-nez nearly flying off. Einstein would shred on the violin, tossing his mane. If some guy like Louis de Broglie, a little Frenchman, were to tap dance too, they could have gone on tour and hit the road. Tonight in Nuremberg, singing and dancing all evening long. Oh. But they were serious people, physicists, so they played Bach. Slowly and sadly. By the way, I didn't mention Louis de Broglie for nothing. He was the third one who tried to save, the classical world. That is, the very physical reality upon which the physics of the 18th and 19th centuries stood. He was also one of the founders of quantum mechanics, and he also tried to save old physics, to find an interpretation of quantum mechanics in which the world would remain objectively existing and causally determined. Because quantum mechanics brought everything down, both causality and realism. In general, old-school physicists believed that there exists an objective reality, independent of our experience. Einstein's most famous phrase about this, slightly modified, is that the moon exists regardless of whether we look at it or not. Observation, they believed, does not change reality, but only confirms it in our eyes. And they believed that our world is continuous, let's say, yes, and not discrete. And that in this world there are trajectories, precise values for speeds or coordinates. You can measure mass, you can measure energy, everything can be measured with any precision. Who is stopping us from improving our instruments and reaching any precision we might want? And in this way, approach a certain precise value of any quantity that actually exists in nature. And if we discover something, they would say, for example, a new planet. Or we open a black box in the game, what, where, when, and see a white ivory ball inside, we draw the definitive conclusion that this planet was already in the sky, and this white ball was in the box before we opened the lid. We simply discovered this white ball, and before that, we just didn't know it was lying there. But it was there, of course. This, of course, formed the foundation of physics. We are discovering a world that already existed before us with all its values and magnitudes. No one even spoke about this explicitly or directly until the advent of quantum mechanics. This a priori assumption seemed so natural that the ball was in the box before the discovery of this ball, and this box took place. Quantum mechanics said that is not the case. And that underlying assumption, which was not even discussed because it seemed so natural, yes, was incorrect. First, quantum mechanics showed that there is a limit to measurement precision, independent of the accuracy of our instruments. In physics, this is called the Heisenberg uncertainty principle. Nature itself just turned out to be blurred. Second, quantum mechanics showed that causality at the fundamental level is replaced by randomness. One cause can lead to a bunch of effects, and predicting exactly what will happen is fundamentally impossible. Only a measurement can show what will specifically happen. If you don't take a measurement, then anything can happen, and this is called a superposition of possible states. The third thing that follows from this, and quantum mechanics has proven it, is that measurable quantities in the quantum world do not exist at all before measurement. It is the measurement as a physical process of interaction, yes, with the system, that assigns a measured value to the object. And our heroes categorically disagreed with this. Einstein said, "Come on, we just don't know something yet about how the world works. So this theory of yours, this newfangled quantum one, it just gives a purely virtual, probabilistic result. It's just that we are at an intermediate stage of science, right? It is just a mathematical trick. We will learn more later, improve the theory, new formulas will appear, but in reality, our world is fatal and deterministic." Where did he get that from? From nowhere. That was his belief, Einstein's, yes. Einstein did not believe in God, but for some reason, he believed in the fatality of the world. Well, he also believed in socialism. From a philosophical point of view, this was, of course, nonsense, but physicists were so used to measuring this way that they didn't even notice this nonsense and believed, in the iron determinism of the world. Although in such a world, evolution isn't possible. Evolution is a child of chance. We know this, yes, from our past lectures. The most amazing thing is that Planck began his physics career back when physics had not even discovered atoms yet. So physicists did not believe in the atomic structure of matter. They laughed at Boltzmann, who was certain of it. They drove the old man to suicide. Physicists seriously believed that matter could be divided infinitely, and that energy, meaning radiation, is emitted as electromagnetic waves, and waves are continuous. I will not talk about the ultraviolet catastrophe now, as we all studied it in school. I will just remind you that, while not believing in atoms at all, Planck empirically, based on experiments, derived the correct working formulas, from which it followed that energy is quantized, meaning energy does not spread in waves, but is emitted in portions, like particles. It's absurd, isn't it? And yet, the fact that electromagnetic radiation, like light for example, consists of waves, had already been proven by experiments with diffraction and interference. Where have you ever seen a sea, for instance, that isn't made of waves, but of some kind of wave particles? It is impossible to even imagine such a thing, because waves are continuous all the way to the horizon, to the left and to the right, and they flow into one another. They are continual, meaning they are continuous, not discrete. And what are discrete objects? Well, ping-pong balls. That is how waves behave. They add up and subtract, creating an interference pattern. And that is how balls or particles behave. The quantization of the world was so displeasing to Planck and so contrary to the conventional views of physicists at the time that once, while walking in the park with his son, when his son asked him, "Dad, what are you working on?" Planck told him, "Son, this is either the greatest discovery since Newton or complete bullshit." He was just talking about his formulas, from which the existence of quanta followed, those indivisible portions of energy, that is, radiation. In physics, let me remind you, traditionally, radiation is called energy. Well, for brevity, let's say. Planck himself believed that these quanta he had invented were just an artificial mathematical trick, which he simply had to use to fit his formula to the experiment, and that in the future, physics would get rid of these very quanta, and his formulas along with them, when people smarter than him entered the field. By the way, Planck himself did not consider himself particularly smart. This story is very well known, but damn it, in a story about Planck, it cannot be avoided. When Planck was wavering about whether to go into science or music to write operettas, he talked about his fate with a professor at the University of Munich. History has even preserved his name for us, Philipp von Joly. There was this jerk, a physicist, who was born back in the Napoleonic era. And this jerk of a physicist said to the 16-year-old kid, our Max Planck, "No problem at all. You'd better go write operettas. That will always be in demand. As for physics, it's done. It's practically finished. Yes, just a few minor details left to clarify. There's nothing left to find there. You won't make any more great discoveries in physics. Everything has already been stolen before us, as they say. Yes." To which Max, a modest kid, replied, "Well, actually, I am not claiming anything. I am not exactly brilliant, you know. I will be happy just to clarify a few details. And a professorship in the future." That is how he assessed himself. And now, on Max Planck's monument, the Planck constant is carved in stone. This is the number that even earned its own letter, just like pi or the number e. It is a fundamental constant of the universe, the minimum quantum of action that defines our entire world. That is how the kid with his operettas suddenly hit it big. It happened in 1874, so that is a quarter of a century before the 20th century, right? And then another 14 years until the First World War, which lasted several years, and then another 20 years until the Second World War, and then another 6 years of the Second World War. And in short, the operetta boy Max from the 19th century died in 1947 after the Second World War. He died a very old man. He was nearly 90, with a tragic fate. His first son, by the way, since we're on the subject, yes, the son to whom he said at the beginning, at the end of the 19th century, in 1900, that he had either made a brilliant discovery or failed miserably. That son of his died in the First World War at Verdun, the famous Verdun meat grinder. His second son died in the Second World War, but not at the front. You see, he was an accomplice in that famous assassination attempt on Hitler. Remember the attempt by that one-eyed Colonel Stauffenberg? The film was made in Hollywood. Who played him there? I think Tom Cruise played Colonel Stauffenberg. Planck's son was also involved in this conspiracy. Planck tried to save him from execution, from the gallows, and wrote letters to Hitler. It did not help. His son was hanged with a piano wire. Although Planck was personally acquainted with Hitler, they had met once before the war. He asked Hitler not to fire the Jewish physicists. But Hitler was a madman, so he lost his physicists. Einstein left for America and wrote a letter to Roosevelt stating that Germany could build an atomic bomb. And that letter, essentially, is what started the Manhattan Project. It was precisely this letter and Einstein's authority that pushed Roosevelt to launch the project to build an atomic bomb. It is bad to be a possessed Führer. Planck also had twin daughters, by the way, which is also an interesting story. They both died. One of them got married and died in childbirth. They were twins, right? And her widower, not being a fool, immediately married the other twin. I mean, they were identical, right? It makes sense. If he liked one, well, there was a second one as a backup. It came in handy. So, he got her pregnant too, and she also died in childbirth. That is what genetics is. Well, Max Planck was certainly upset. He lost his wife too, who had borne him all four of these children. His wife died, I believe, in 1909 from tuberculosis. Oh, how fashionable that was in those days. Oh, everyone walked around so pale, coughing blood into lace handkerchiefs. That was the early 20th century. And Planck, by the way, not being a fool after his wife died, went and married his niece. Of his wife's niece. Well, I would have married some niece too, but I don't have any nieces. There is absolutely no one to marry. But on the other hand, he lived with his second wife until his very death. His house was destroyed during an Allied bombing. He lost everything, his notes, his library, and he wandered with his wife toward the American occupation zone. I would have gone there too in his place. Not to the Soviets, surely. Even if I were a Soviet citizen and had been captured by Germany, I would still have walked on foot from German captivity to the West, far away from Conrad Stalin. Do you know why? Because freedom is more precious than one's homeland. Remember this principle, my children. Freedom is more precious than one's homeland. In short, Max Planck, lost everything by the end of his life. His entire life was one continuous loss. And against the backdrop of these external losses, an inner tragedy unfolded. The entire familiar physical world to which he had dedicated his life was breaking down. Having renounced music, yes, and that very world, which physicists were accustomed to considering real, turned out not to be so. This objectively existing world, that is, one independent of the observer, turned out to be dependent on the observer. Max Planck, who himself laid the foundation of quantum mechanics with his quanta, then spent many years trying to get out of it. He worked on his equations, tried hard, sat up at night, trying to bring his equations back to a classical form without success. And Einstein, you see, also received the Nobel Prize for proving in his work on the photoelectric effect that light is not just a continuous wave, which was already known, but also particles, photons, meaning that radiation travels in chunks somehow. So he confirmed Planck's findings. And Louis de Broglie, who was just here tap dancing on tour, went even further. He stated that not only do electromagnetic waves have a corpuscular nature, but particles themselves, for example, electrons, are also waves at the same time. This was later proven in double-slit experiments. And this very Louis de Broglie, who said and proved this, he desperately tried to save realism in physics, that is, the edifice of classical physics, from his own assault. He started coming up with some sketchy schemes, pilot waves and other unthinkable nonsense. And all of this was in vain for all three of them. All those famous arguments between a terrified Einstein and the phlegmatic Bohr at the Solvay conferences, when Einstein couldn't sleep at night and time after time, attempted various thought experiments trying to prove that there are, after all, some hidden variables in the world that we do not yet know about, which strictly determine the electron's behavior and exactly where it will land. And when we study it and make predictions, new formulas will appear. Einstein was certain that in physical experiments we measure what objectively exists in nature. As I already said, yes, whether we measured it or not, it is there. A white ivory ball lies in a black box. Otherwise, the very physical reality that physics has been studying for 200 years will collapse. And Bohr objected to him. "You are already tiresome with this physics. Physics does not study the world," he said, "as such, but the results of our measurements. And that is it. That is all of physics. Whatever we measured is what we look at. Physicists have nothing else on hand. And if we haven't measured anything, it's foolish to even argue whether nature has that value or if we created it with our measurement. That is already philosophy. Let the philosophers deal with it. They have nothing better to do anyway. But we have formulas, and we use them to calculate. Everything adds up when we calculate. And what lies behind these formulas, how to interpret them, that is not our business. Shut your trap and calculate, don't think. Let the horse think. It has a bigger head. That is what Bohr said. The 20th century showed that Bohr was right in this dispute. There are no hidden parameters that could be studied even deeper to predict the behavior of an electron. The world is truly not fatalistic. A measured parameter in the quantum world does not in fact exist until it is measured. The measurement creates the measured value. And also, by the way, just as Einstein predicted, such a world must be non-local. And that is exactly what it turned out to be. What does non-local mean? It means that if two entangled particles, and entangled particles are those that have collided and linked their fates, right? And then they can be moved to opposite ends of the universe, and you can perform a measurement on one particle, thereby creating the measured parameter. And at that very same moment, at the other end of the universe, this same parameter is created in the other particle. If we measure spin up here, then we get spin down there, 1/2, right? Meaning the effect was transmitted faster than the speed of light, instantly, at any distance. Because from the point of view of quantum mechanics, these two particles are described by a single wave function, because they are entangled and represent a single object. And a little later, we will see that the entire universe represents a single object. This, in a way, hints to us that space and time are not the most fundamental things in the world. There is something more fundamental. That is the first point. Second, the mathematical apparatus of quantum mechanics. It does not assume any wave function collapse, no function shrinkage, no reduction. What does that mean? So, an electron is flying, right? Where will it land? To the left, there, down, or up? We do not know. On the screen, yes, here or here, we do not know this. The state of the electron is described by a wave function and represents a superposition of two states. It hits here or it hits here, right? Superposition is just a sum, in plain language. It is written with a plus sign, linearly. This is what it looks like in simplified terms. The state of the system equals, with probability A, event x1 will occur, meaning the electron will land on the left, let's say, plus with probability B, event x2 will occur, meaning the electron will land on the right. That is all. And this superposition must be preserved. Well, the details are in this book. Why do we always see only one result then? It hit either here or here, this electron. That is the real world. It collapses the wave function. When we place a screen under a flying electron to take a measurement and find out where on the screen it lands, transforming from a flying cloud into a point, a particle, the electron's wave function, this cloud, is reduced, instantly collapsing into a point, into a single outcome. Although in mathematics, it just doesn't happen that you can arbitrarily throw away half an equation. But in the real world, which physicists are, well, used to calling classical, yes, only one option remains. And this superposition disappears somewhere. Well, perhaps we shouldn't worry about this. Maybe the formulas of quantum mechanics only apply to the micro world? No, we live in a quantum world. We are all made of particles. And so to move away. So, from the micro world, electrons and other quanta, and to bring this fundamental question to the level of the macro world, Schrödinger once came up with this famous thought experiment with his cat, right? Well, I will briefly remind you in case anyone has forgotten. A cat is sitting in a box. Inside the box, there is an atom that has a 1/2 probability of decaying within a minute. If it decays, a hammer breaks a vial of cyanide. The cyanide spreads throughout the box, and the cat dies. If the atom has decayed, the cat is dead. If the atom has not decayed, and the probability is 1/2, the cat is not dead. What is the essence of this thought experiment? Until we open the lid, we are obligated from the perspective of quantum mechanics. That is, if quantum mechanics is correct. And it is correct. We have no more precise or general theory in physics. Quantum mechanics is practically ultimate. So, we are obliged to describe the state, the total state of this whole system, including the cat, as a superposition of states. Cat alive plus cat dead. Because the state of the radioactive particle becomes entangled with the state of the hammer, breaking the vial of cyanide, the flask with the gas, and the cat itself. That is, the wave function must include, yes, both the box and the cat's particles. And furthermore, when the researcher opens the lid to look at the result, the state of the box with the cat must become entangled with the state of his eyes, with the state of the optic nerve, along which this signal travels to the brain, and the brain itself, because the brain also consists of particles, of quanta. That is, the superposition must be preserved. So where does it go? Why does the state of the system suddenly reduce to one specific option, either alive or dead? After all, the mathematics of quantum mechanics, I repeat, does not imply any reduction. Why then do we always see only one result, either alive or dead? And see in this case means are aware of. Not when the impulse is traveling from the retina to the brain along the optic nerve, and we have not yet realized if the cat is alive or dead. But at the moment we perceive the result, the reduction occurs. That is the moment when consciousness appears in physics. That is the reason for the reduction. Consciousness is the only thing in the universe that is not made of material particles. It is immaterial and therefore free from both physics and mathematics. We can imagine anything we want. That is, we live in an invented world. In a world of consciousness, everything you see around you is not even a product of your consciousness, but is your consciousness itself. If this world goes out, it means your consciousness has gone out. And if your consciousness goes out, your whole world will go out with it. It is one and the same. The world that physicists studied and called real turned out to be entirely made up. As Hindus say, the whole world is Maya, that is, our illusion, a pure appearance. This world is a dream you are having, Eastern philosophy says. Yes, a dream, only while awake. It is no wonder that a huge number of physicists, the physicists of the 20th century who studied quantum mechanics, rushed into mysticism and Eastern philosophy. Even though Bohr forbade interpreting quantum mechanics, telling them to just blindly calculate and get results, without thinking about what lies behind the formulas. This also went against the entire history of physics, because physics had always worked with visual models, inventing lines of force, material points, and trajectories. People have always been interested in what lies behind the formulas. They drew models of what is actually happening. But quantum mechanics said, there is no actually. Quantum reality is the formulas themselves, and what you are used to calling reality or the physical world is the world of your measurements. Shooting began. You see, studying the Upanishads, Heisenberg became fascinated by Indian philosophy. So, Planck, Pauli, Jordan, Dirac, Bond, and not Bohr, Everett, Einstein, all of them delved to one degree or another into studying philosophy. Even Bohr, who discouraged everyone from looking, behind that curtain of mystery, right? Was no stranger to philosophy himself, studied it very closely, and even placed the Eastern yin-yang symbol on his family coat of arms. Well, when the king made him a nobleman, the king of Denmark made him a nobleman, knighted him for his services to physics, he had to come up with a coat of arms for himself. And he came up with this coat of arms. And in the end, Everett reached a consistent conclusion. There is no reduction. It only seems that way to us. All events in the quantum world must exist simultaneously. This was called the many worlds interpretation of quantum mechanics. It is called the Everett many worlds interpretation. In my view, this is a very poor name that is misleading, because people interpret it as a branching of worlds, as if the universe splits at every moment, and then the fates of these universes diverge. Well, that is not the case at all. Such a large object as the universe cannot appear in the blink of an eye, as it would violate the law of conservation of energy. And where would it even appear? In reality, In the quantum world, which is completely unimaginable to us, everything happens all at once. All the universes are already there in one place, right here. And they exist in a state of superposition simultaneously. Nowadays, more and more physicists are leaning toward Everett's view because, well, the logic and mathematics of quantum mechanics are inexorably pushing them there. But back when he first proposed it, Everett, nobody accepted him, almost right, except for Wheeler, I think. No one understood. They laughed at him, mocked him. As a result, Everett left physics, ended up an alcoholic, and died. So why is it that we don't see any superposition, but only see one version of the universe, right? The cat is either alive or dead. Either I go into music to write operettas, or I go into physics. It's because we are this universe. All of it. Consciousness and the world are two sides of the same coin. If there is no world, there is no consciousness, because it has nothing to process, right? And if there is no consciousness, well, for example, in those hypothetical universes with different physics, where the existence of complex systems is impossible, there is no one there to witness the existence of that universe, no one to perform a measurement. There is no one to realize this universe. By the way, outside our universe, there is nothing, no external objects, right? Therefore, there is nothing to collapse our universe, nothing to reduce it, to collapse it into a classical state. Therefore, from its very birth, and it was born, simply speaking, from a single singularity point, when all particles were one, everything reacted with everything, and then scattered to different ends of our non-local universe, right? That is why our entire universe is still described by a single wave function. Once again, because there is no one outside to collapse it. That is, it exists in a superposition all at once, yes, with all its possible outcomes. And every possibility, every version of how events unfold, whether an electron fell here or there, is a separate classical world. So we, each of us, are our own classical world, which was once called the real physical world. But now it is clear that it is a product of measurement, that is, a product of realizing the result. Zen Buddhism says that in the world, there is only consciousness. I should do a separate episode comparing quantum mechanics in the Everett-Minsky-Nikonov interpretation with Zen Buddhism sometime. I will do that eventually. That is enough for today. Go and manifest your own universe.